Speeding at Sea, it's me, Z. Hello, everybody. Welcome to episode 1 of the machine learning series. Um, I am so excited to share this with you guys. What's even more exciting is that Google just dropped their brand new update of the machine learning crash course today. If that isn't a sign, I don't know what is. Um, hello. First off, class, let's do a little bit of attendance. Hello, Penbu. Hello, Space Guy Rai. Hello, Tokyo 393. Hello, Ricardo Berrigan. Tokyo, I hope you can somehow passively absorb this information at 4 a.m. Or no, that was White Fang. Both of you guys. And then hello Mind Force, hello Till Aspera, hello Luwak, hello Crypta, hello Bob 10, hello PogChamp Senpai, hello. The whole class is here. We have perfect attendance, guys. I hope everybody's been having an epic day. I had an epic day when I realized that the new crash course dropped today, which was amazing. Yes, so before we get started, a few things. As many of you guys may know, this is unfortunately my last week of live streams before I will be gone for a few weeks due to traveling. So let's make the most out of our last week together. I'm definitely going to continue this series when I return. So, Orbeez, your homework is to review these videos while I'm gone. And speaking of, I will be compiling some notes based off of the things we learned today. So hopefully that will give you guys enough review material. In addition, I am also a total beginner. If you guys are also a beginner, please let me know in the chat. I feel like I should maybe know this in advance, but I am totally new to this. Feel free to ask questions, though I will also be part of the learning process, so we can grow and learn together. How about that? Hello, Aegis Slayer. All right, so do you guys just want to jump into it? Hello, Tokyo 393. I am not new to programming. I've done a lot of Python, C++, though I feel like I think Google's course here is actually more based off of the conceptual part of machine learning, which I am definitely new to. It'll be really interesting if they also have some coding exercises. But we're going to start at the very beginning. So if you go to the link in the chat, you can follow along. We're going to start at number 1. Which is Introduction to Machine Learning, right here. Okay, so let's get started. Okay. And also, if you enjoyed this series, be sure to update, subscribe, do all of the class duties. And yeah, no, I am basically doing this part-time, so hopefully when I return back, I will have enough time to continue live streaming. Maybe not at the rate that I did over this summer, but hopefully at a similar rate. We'll see. Okay, let's just jump straight into it. Introduction to Machine Learning. Welcome to Introduction to Machine Learning. This course introduces ML concepts. This does not cover how to implement ML or work with data. Oh, hello, Cyano Acre. Hello, Teach Z. Actually, that reminds me, you guys should think of a cool name for this series. So far, I'm just thinking like ML with Z or machine learning with Z, but what do you guys think? Okay, what is machine learning? So, ML powers some of the most important technologies we use, from translation apps to autonomous vehicles. This course explains the core concepts behind ML. ML offers a new way to solve problems, answer complex questions, and create new content. ML can predict the weather, estimate travel times, recommend songs, blah, 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 blah. Basically, it can do a lot of epic things. In basic terms, ML is the process of training a piece of software called a model to make useful predictions or generate content from data. For example, if we wanted to create an app to predict rainfall, we could use either a traditional approach or an ML approach. So with a traditional approach, we create a physics-based representation of the Earth's atmosphere and surface, computing massive amounts of fluid dynamics equations. That just sounds very, very difficult. Think about all of the amounts of fluid, amounts of like molecular level modeling you'd have to do. That sounds really hard. Using an ML approach, we would give an ML model enormous amounts of weather data until the ML model eventually learned the mathematical relationship between weather patterns that produce differing amounts of rain. So using existing data to predict patterns. So we would then give the model the current weather data and it would predict the amount of rain. Also, I am going to stay away from watching the videos that are on this course. So please feel free to go through them in your own time. This is mainly to avoid copy strike. I chatted with another coding VTuber. Her name is code_life. I think I've retweeted her posts a few times here and there. She's also a great machine learning coder. She's the one who suggested this course to me. And she was also saying that it's probably not a good idea to show these videos on live stream due to copy strike. But I think this is all right since we're basically going through a website. Space Guy Ride, machine learning A to Z. Oh, that's so smart. I love that. That's adorable. Okay, first check. Oh, is this a multiple choice? Okay, I guess so. What is a model machine learning? A model is a smaller representation of the thing you're studying. A model is a mathematical relationship derived from data that an ML system uses to make predictions. A model is a piece of computer software. I mean, this seems pretty straightforward, just based off of the discussions that we had about the rain. But a model is a mathematical relationship derived from data that a machine learning system uses to make predictions. So let me jot that down real quick. So a model is I don't know if you guys can hear my sounds as I write. Mathematical relationship derived from data that an ML system uses to make predictions. So ML is really all about predictions. Types of ML systems. ML systems fall into one or more of the following categories based on how they learn to make predictions or generate content. Supervised learning, unsupervised learning. Oh, okay, wow. Reinforcement learning and generative AI. I think there's actually a part of this course that focuses on generative AI. This course goes into depth into a wide variety of different topics like decision forests and stuff like that. So plenty of content for us to go through. Okay, so supervised learning. So supervised learning models can make predictions after seeing lots of data with the correct answers and then discovering the connections between the elements in the data that produce the correct answers. So this is like a student learning new material by studying old exams that contain both questions and answers. Huh. I don't know if a lot of you guys had this, but when we had like the SAT, ACT like back in high school, oh my god, that sentence re-sparked some insane trauma in me. Once the student has trained on enough old exams, no, the student is well prepared to take a new exam. So we are machine learning. These ML systems are supervised in the sense that a human gives the ML system data with the known correct results. Okay, so I guess the way to summarize this is, so basically making predictions after seeing lots of correct data. Haha, same. Yeah, no, that was a dark time. The two of the most common use cases for supervised learning are regression and classification. A regression model predicts a numerical value. Okay, so regression, numerical value. For example, a weather model that predicts the amount of rain is a regression model. So future house price So we can predict the price of a home, future ride time, which can predict the time in minutes and seconds to arrive at a destination. Okay, so regression models is all about predicting numeric values. I actually didn't know that. I thought regression had something to do with like, I don't know if you guys have heard of like regression lines. I guess those are also all about the numbers. Classification. Classification models predict the likelihood that something belongs in a category. Unlike regression models whose output is a number, classification models output a value that states whether or not something belongs to a particular category. This reminds me of a lot of those AI things where they categorize if an animal looks like a cat or a dog or something like that. Classification models are divided into two groups, binary classification and multi-class classification. Okay, so we have regression, we have classification models, which are basically predicting the category. So you can either do binary classification, outputs a value from a class that contains only two values, for example, rain or no rain. So, and then multi-class outputs a value from a class that contains more than two values, a model that can output either rain, hail, snow, or sleet. That makes sense. Okay, another video here you guys can watch. I thought it was similar to the concept of regression test in code. Ah, that actually brings up a good point. I think it is related to regressions. My understanding is that you fit some f of x known, and evaluate for a function f on x unknown. Yeah. Also, this is a good hydration check. Make sure you guys are staying hydrated to power your big brains. Okay, so check your understanding. If you wanted to use an ML model to predict energy usage for commercial buildings, what type of model would you use? Regression, because energy usage is a number. Yeah. Kilowatt hours. That's a really long unit. There's some like really funky units for energy usage from what I've heard, beyond kilowatt hours. Apparently it has to do with the way that the units align. So before you know it, you have like really long names that combine two types of units to get the correct unitary value. So in this case, it's watt hours. You're multiplying power by time. But in other cases, you have to multiply many other units together. All right. So that was all supervised learning. So now we're going into unsupervised learning. So unsupervised learning models make predictions by giving data that does not contain any correct answers. So data does not contain correct answers. An unsupervised learning model's goal is to identify meaningful patterns among the data. In other words, the model has no hints on how to categorize each piece of data, but instead it must infer its own rules. A commonly used unsupervised learning model employs a technique called clustering. The model finds data points that demarcate natural groupings. Ooh. So we have clustering. So in this case, we have cluster 1. So these are different data points, and it seems like it's sort of finds like the natural groupings of each color. Cool. Clustering differs from classification because the categories aren't defined by you. For example, an unsupervised model might cluster a weather data set based on temperature, revealing segmentations that define the seasons. You might then attempt to name those clusters based on your understanding of the data set. So ML's clustering similar weather patterns: snow, rain, sleet, no rain. And so it sort of finds these boundaries. I see. So in this case, we aren't given a correct answer. In this case, we are just clustering these things based off of their category. So what distinguishes a supervised approach from an unsupervised approach? So yeah, that was just what I was saying. A supervised approach is given data that contains the correct answer. The model's job is to find connections that produce the correct answer. So yeah, its job is to find groupings in the data. So it's different types of applications. But I'm wondering, is there a way to sort of find groupings based off of the classification approach that we did before? The classification approach we did for supervised learning predicts the categories. But maybe in that case, we're given a correct answer, like the exact properties of each category. So when we assign a value and say, like, this goes into this category, we know that that is the correct answer. Whereas here, we're just determining categories based off of like where the points are. Maybe that's the big difference. Yeah, I think we define the categories also. PogChamp Senpai, yeah, that makes sense. Okay. Next up, reinforcement learning. Whew. I'm jotting down notes for you guys, but I'm running out of colors. Reinforcement learning. Reinforcement learning models make predictions by getting rewards or penalties based on actions performed within an environment. This is like me in my everyday life. A reinforcement learning system generates a policy that defines the best strategy for getting the most rewards. Reinforcement learning is used to train robots to perform tasks like walking around a room, and software programs like AlphaGo to play the game of Go. I see. I guess that's also how they make those like really cool chess robots. And then we have generative AI. Generative AI, which creates content from user input. For example, generative AI can create unique images, music compositions, and jokes. So this is creating content. Can summarize articles, how to perform a task or edit a photo, can take a variety of inputs and create a variety of outputs, can take an image, and so it basically can go from different types of inputs and outputs. Yeah, text to text. I mean, I think we're all pretty familiar with generative AI now with ChatGPT and wow, this is a really interesting video. Nowadays, those text to video AIs have gotten like really, really powerful. I've heard of a lot of really bad things that have been happening as a result of AI though. Right, so it can also build code, it can create image to text. How does generative AI work? At a high level, generative models learn patterns in data with the goal of producing new but similar data. So are initially trained using an unsupervised approach where the model learns to mimic the data it's trained on. The model is sometimes trained further using supervised or reinforcement learning on specific data related to tasks. Wow, so this basically combines everything. Yeah, cool. So we learned about all of these different terms. Mainly we talked about what is supervised learning, unsupervised learning, reinforcement learning, and generative AI. All right, next up. Supervised learning. So this is a whole new chapter. Supervised learning. So supervised learning's tasks are well defined and can be applied to a multitude of scenarios, like identifying spam or predicting precipitation. So supervised machine learning is based on the following core concepts: data, model, training, evaluation, and inference. Okay, so data is the driving force of machine learning. Data comes in forms of words and numbers stored in tables or as the value of pixels and waveforms. So we can have many different types of data. Are made up of individual examples that contain features and a label. You can think of an example as analogous to a single row in a spreadsheet. Features are the values that a supervised model used to predict the label. The label is the answer, or the value we want the model to predict. In a weather model that predicts rainfall, the features could be latitude, longitude, temperature, humidity, cloud coverage, wind direction, and atmospheric pressure. The label would be rainfall amount. So the label is sort of what each data value is, I guess. Two labeled examples. Okay, so the features are here. Oh, and then we have the label on the right. In contrast, unlabeled examples contain features, but no label. So the label's the answer. Oh, so the label is what we want to predict. So this one just has the data. Okay, cool. So labeled and unlabeled. Dataset characteristics. A dataset is characterized by its size and diversity. Size indicates the number of examples. Diversity indicates the range those examples cover. Good datasets are both large and highly diverse. Yes, some datasets are large and diverse. However, some datasets are large but have low diversity, and some are small. Okay, so we can get various different types of datasets. That seems to make sense. For instance, a dataset might contain 100 years worth of data, but only for the month of July. Using this dataset to predict rainfall in January would produce poor predictions. Yeah, that checks out. Okay, I think that's pretty self-explanatory. Basically, we have different types of data. Some are good, some are not so good. So what attributes of a dataset would be ideal to use for machine learning? Well, we definitely want to go for a large dataset with very large diversity so that we can predict another attribute. Yeah. A large number of examples that cover a variety of use cases is essential for a machine learning system to understand the underlying patterns in data. Yep. A dataset can also be characterized by its number of features. For example, some weather datasets might contain hundreds of features, from satellite imagery to cloud coverage values. Other datasets might contain only 3 or 4 features, like humidity, atmospheric pressure, and temperature. Datasets with more features can help a model discover additional patterns and make better predictions. However, datasets with more features don't always produce models that make better predictions because some features might have no causal relationship to the label. So we can have basically like many columns, many different types of features, but not all of them may have a relationship to what we're trying to predict. So in that case, I guess having many features might be a disadvantage sometimes. Could it distract from the dataset? Oh, also, I should check the chat more often. I saw a wild AI video yesterday. It ended with a guy flying away like a helicopter. If you guys have time, you should also Google AI videos of gymnastics. It's like the most disturbing, weird thing that I've ever seen. Like, the AI does a pretty good job of, like, capturing the general motion of what you'd expect. But it just doesn't do a good job of, like, placing the body features. This reminds me of our dataset of, oh, do you mean, like, habitable planets? Dataset is n equals 1. No, exactly. I think that's actually really interesting because, that's why people are thinking we could have, like, methane-based life or even weirdly, like, silicon-based life. Which is really weird to think about. Just because we're on Earth doesn't mean that that's the case. Like, water-based and oxygen-based life is not the case. Or carbon-based life isn't the case in other planets. More features requires a more accurate model. That's true. Alright, let me take a sip of orange juice. I know, I have an interesting beverage every time around. I actually freshly squeezed these oranges right before the live stream so I can drink it. It's really good. All right. Let's go to the model. In supervised learning, a model is a complex collection of numbers that define the mathematical relationship from specific input feature patterns to specific output label values. The model discovers these patterns through training. Checks out. Yeah, no, it's very delicious. Vitamin C for Z. Yep, gotta get that vitamin C. Training. Before a supervised model can make predictions, it must be trained. To train a model, we give the model a data set with labeled examples. The model's goal is to work out the best solution for predicting the labels from the features. Okay. The model finds the best solution by comparing its predicted value to the label's actual value. Okay, so what it does is that it predicts and then compares to what it actually should be. So based on the difference between the predicted and actual values, this is the loss. I'm laughing because it reminds me of that one like meme that's called loss. Okay, the model gradually updates its solution. In other words, the model learns a mathematical relationship between the features and the label so that it can make the best predictions on unseen data. Okay, cool, so it uses loss. Okay. For example, if the model predicted 1.15 inches of rain, but the actual value was 0.75 inches, the model modifies its solution so its prediction is closer to 0.75 inches. Okay, cool. Isn't this basically sort of like a penalty? Well, I guess they're not actually penalizing the model for getting it wrong. They're just adjusting it. They're training it. After the model has looked at each example in the data set, it arrives at a solution that makes the best predictions for each of the examples. Okay. Crypto, oh god, that was horrifying. Yeah, to any Orbeez who decide to watch, a bit of a warning if you ever Google AI videos of gymnasts. Gymnasts. Watching a 4-dimensional gymnast with my 3-dimensional eyes. Yeah, it's very odd. If you like that, maybe I should do a 5D chess stream sometime. The model takes in a single labeled example and provides a prediction. Okay. The model compares its predicted value with the actual value and updates its solution. Okay, the model repeats this process for each labeled example in the dataset. Okay, so there can be multiple, I guess we can have multiple values that we are predicting, but the same label, so the same type of feature that we are predicting, just multiple times. And so you're updating the model. In this way, the model gradually learns the correct relationship between the features and the label. This gradual understanding is why large and diverse data sets produce a better model. The model has seen more data with a wider range of values and has refined its understanding of the relationship between the features and the label. During training, ML practitioners can make subtle adjustments to the configurations and features the model uses to make predictions. For example, certain features have more predictive power than others. Therefore, ML practitioners can select which features the model uses during training. For example, suppose a weather dataset contains time of day as a feature. In this case, an ML practitioner can add or remove time of day during training to see whether the model makes better predictions with or without it. Ah, I see. So maybe that's an interesting way of capturing which features actually have a relationship with the label that we're trying to predict. PogChamp Senpai. It's basically cheating at the start, knowing the result, it perfects his model of prediction. Yeah, no, I feel like this is really dependent on having the correct answer. Like, what if you want to make new discoveries or find new relationships? Maybe it can also, I guess if you have a not large and diverse enough data set, you can predict and find new patterns that weren't there before by training the model to predict and seeing what the model has sort of learned while predicting new values for its labels. Evaluating. We evaluate a trained model to determine how well it learned. When we evaluate a model, we use a labeled data set, but we only give the model the data set's features. We then compare the model's predictions to the label's true features. All right, let's look at this diagram. Use a trained ML model to predict a value from a given data set with labeled examples. Okay. So we then compare the predicted values with the actual values. So this red box here is the trained ML model. Okay. Depending on the model's predictions, we might need to do more training and evaluating before deploying the model in a real-world application. Okay, cool. Why does a model need to be trained before it can make predictions? A model doesn't need to be trained. Yes. No, a model needs to be trained to learn the mathematical relationship between the features and the label in a dataset. A model needs to be trained so it won't require data to make a prediction. I think it's definitely the second one, because we're finding the relationship between the features and the label. After all, the training involves using the features and making predictions of the label. There we go. Inference. Once we're satisfied with the results from evaluating the model, we can use the model to make predictions or inferences on labeled examples. In the weather app example, we would give the model the current weather conditions, the temperature, atmospheric pressure, and relative humidity, and it would predict the amount of rainfall. So the inferences are then our final predictions. PogChamp Senpai. It's another kind of model. It should be unsupervised in that case, I think. Oh, you mean the example that I gave earlier? Yeah, no, I see. Yeah, no, that makes sense. This is just for supervised learning. At least like this section. Yeah. Oh, guys. Orbeez, we have a test. We have a test. The following questions help you solidify your understanding of core ML concepts. Predictive power. Supervised ML models are trained using datasets with labeled examples. The model learns how to predict the label from the features. However, not every feature in a dataset has predictive power. In some cases, only a few features will actually have a relationship with the label. In the dataset below, use price as a label and the remaining columns as the features. So here we have color, miles, height, gearbox, make, model, length, tire size. So these are all like car features. And using that, we're supposed to determine the price. So which 3 features do you think are likely the greatest predictors for a car's price? Miles, gearbox, make, model, tire size, wheelbase, year, color, height, make, model, year, miles. I actually don't really know much about cars, but from the top of my head, the make, model is definitely a factor. Miles, I mean, if there's more miles, then a car would be cheaper because it probably wouldn't go as further. But what exactly is a gearbox? This is my weakness. Would you say 1, PogChamp Senpai? Do they mean year as like current year? I feel like in that case, then maybe the gearbox, miles, and make, model would make the most sense. Yeah, I think that would probably be better. Miles, gearbox, make, model. All right, let's try this. Womp womp, ruh-roh. The gearbox isn't a main predictor of what even is, hold up, I'm going to Google this real quick. Sean P. 4? What is a gearbox? Gearbox car. I Googled gearbox and I got this weird badminton thing. Oh, it's literally the gears. It's literally the gears. 4? 4? Does everyone think 4? No, you're good. You're good. Even I don't know. Make, model, year, miles. Let's try that. Okay. Make, model, years, and miles are likely to be among the strongest predictors for its price. I feel like, but isn't miles the same as year? Or maybe it's like, oh, like a 2010 Toyota Corolla versus like a 2015 Toyota Corolla. Maybe that's what it means. So even if it has very few miles, if it's an older car, it's not good. Supervised and unsupervised learning. Based on the problem, you'll use either a supervised or unsupervised approach. For example, if you know beforehand the value or category you want to predict, you would use supervised learning. However, if you wanted to learn if your dataset contains any segmentations or groupings, you use unsupervised learning. So suppose you had a dataset for users for an online shopping site and it contained the following. Last purchase amount, years since sign up, number of purchases, number of coupon usage, education, marital status, and income. So if you wanted to understand the types of users that visit the site, would you use supervised or unsupervised learning? So if you had a data set of users for an online shopping website, you're trying to predict which class a user belongs to. Well, what's sort of the purpose of running this? I think it would be better to categorize the users, but if we do the categorization one here, would that categorize the users by each of these different features? Since I feel like we're maybe not trying to exactly predict the class that a user belongs to. Years since sign up. Maybe it would be good to find groupings of related examples, since we aren't necessarily trying to have a category to predict. Maybe this could have other relationships, like maybe the age of a user. I think I'm going to go with unsupervised learning. Income could be a final label. We could categorize people on income and understand what's our targets. Yeah, no, that would also make sense. This is interesting because I feel like you could sort of go about it either way. You can sort of group users by different categories. Like, what if you want to see, like, how much education does someone have? Or are they more likely to be, like, a specific gender? Supervised learning, Would it be better to try supervised learning and then try unsupervised learning? Maybe we should go with that. Womp womp. In supervised learning, the dataset must contain the label you're trying to predict. In the dataset, there is no label that refers to a category of user. PodChamp Senpai, I think I'll have to give you an F. No, I'm just joking. I feel like even I was really lost on this question. Must contain the label you're trying to predict. In the dataset, there is no label that refers to a category of user. So if we do unsupervised learning, I see. We can create our own names for each cluster. So I guess when I was like asking, what are we trying to find here? Or what is sort of the goal of this? Unsupervised learning would help us find like what is the goal. I guess like to compare as before, like we're trying to find the correct answer. Or we don't have a correct answer. We're trying to create these categories to describe the data. Whereas for supervised learning, we have a correct answer that we're trying to predict. All right. Suppose you had an energy usage data set for homes with the following columns: square feet, lat long, year built, kilowatt hours per year. What type of ML will you use to predict? So in this case, you would want to predict the kilowatt hours per year, so that would be supervised learning. Supervised learning trains on labeled examples. In this dataset, kilowatt hours used per year would be the label. Yep, because that is the value you want the model to predict. Suppose you had a flight dataset with the following columns. Okay, departure, airport, destination, date, time of day, so forth. If you wanted to predict the cost of a coach ticket, would you use regression or classification? So in this case, we would want to do the cost, which is a number, and earlier it said that regression is predicting numerical values. So regression it is. There we go. We're zooming through these now. Based on the data set, could you train a classification model to classify the cost of a coach ticket as high, average, or low? Classify the A classification model would help us categorize. No, a classification model only predicts two categories. No, we saw earlier that we could have two types of classification models. The one that's like either this or not this, or we could do one where it's multiple categories. It was like multi-class. Yes, but we'd first need to convert the numeric values in the coach ticket cost column to categorical values. Yes, but we'd first... Okay. No, it's not possible to create a classification model. The coach ticket cost values are numeric, not categorical. I think it is possible for us to... Wait, the coach ticket cost. So based off of this. Okay. As high, average, or low. It's not possible to create a classification model. The coach ticket cost values are numeric, not categorical. But I think we could still classify a cost by, for example, like what we saw earlier when we plotted it, we would need to categorical values. What does that mean? Categorical values? No, it's not possible to create a classification model. The coach ticket cost values are numeric. What? Wait, let me give this some thought. I'm pretty sure that, let me just hop back to some... I think we could definitely do it. I'll just click the center value for now. Okay. What does it mean by categorical values? It's possible to create a classification model from the dataset. You would do something like the following. Find the average cost of a ticket from the departure airport to the destination airport. Determine the thresholds that would constitute high, average, or low. So you would have to find the thresholds. That's what it means by finding the categorical values. Compare the predicted cost to the thresholds and output the category the value falls within. That makes sense. Training and evaluating. After we've trained a model, we evaluate it by using a data set with labeled examples and compare the model's predicted value to the label's actual value. Select the two best answers for the question. If the model's predictions are far off, what might you do to make them better? Retrain the model, but use only the features you believe have the strongest predicted power for the label. You can't fix a model, no. Try a different training approach. For example, if you use a supervised approach, try an unsupervised approach. Retrain the model using a larger and more diverse data set. I think definitely the last one. Okay. Models trained on datasets with more examples and a wider range of values can produce better predictions. Okay, that makes sense. Because the model has a better generalized solution for the relationship between the features and the label. 1 and 4? Yeah, I think it is possible to retrain it. I don't think it would make sense for us to do a different training approach because that would give us a different objective. So let's try that. Okay, yay. Retrain the model with fewer features, but that have more predictive power, can produce a model that makes better predictions. All right, great. Oh, wow, we just finished the intro to machine learning. Oh, and hello, Vagador Galas. I don't know how to say your name, but hello there. We just finished the intro to machine learning, which means that we are ready to jump into the machine learning crash course. This should all be at the message that I've linked at the very top. Here, let me add a stream marker here. Okay, cool. So this is going to go pretty in depth. So we're going to first start with linear regression. So this model introduces linear regression concepts. So I think this is going to take what we just learned to a much more deeper and maybe mathematical level. So the learning objectives is to explain a loss function and how it works, define and describe how gradient descent finds the optimal model parameters, describe how to tune hyperparameters, to efficiently train a linear model. Reminder for class to also hydrate. Hydrate or dihydrate. Okay, linear regression is a statistical technique used to find the relationship between variables. In an ML context, linear regression finds the relationship between features and a label. So we just reviewed those. So the features and what we're trying to predict, the label. Nikki, yes, linear regression. Yes, we're getting into it. For example, suppose we want to predict a car's fuel efficiency in miles per gallon based on how heavy the car is, and we have the following data set. So if we plotted the points, we get this. Okay, it looks like a pretty downward trend, so the more pounds we have, the miles per gallon decreases. Okay, that makes sense. So as the car gets heavier, its miles per gallon rating generally decreases. So we could create our own model by drawing a best fit line. There we go, the linear regression, the regression line. Best fit line through the points. A best fit line drawn through the data from the previous figure. Linear regression equation. In algebraic terms, the model would be described y equals mx plus b, where we're describing a relationship between x, pounds, and y, miles per gallon. Vagador, play a game. I don't understand what you speak. I'm sorry, but this is a classroom setting, educational only. Although, if you want to play an epic game, I was thinking about playing 5-dimensional chess sometime. That would be really funny, really deep, big brain stuff. And it has time travel, which I think is pretty epic in chess. We write the equation for linear regression model as follows. Okay, so y prime is the predicted label, the output. So now we're changing our y equals mx plus b into this new format, where we have y prime, the predicted label, the output, and then b is the bias of the model. Bias is the same concept as the y-intercept in the algebraic equation for a line. In machine learning, bias is sometimes referred to as W0. I guess why is it W1 here? Oh, because the bias is W0. Okay. Bias is a parameter of the model and is calculated during training. So W1 is the weight of the feature. Weight is the same concept as the slope m in the algebraic equation for a line. Weight is a parameter of the model and is calculated during training. x1 is a feature, the input. Okay, so we're basically predicting the label, which is y prime, with our feature, x1. Great. Oh, this is great. Of course they had to change the letters. Yeah, no, why couldn't they just stick with like mx plus b? I mean, they kept b, and they mostly kept x. A mathematical representation of a linear model. Okay. In our example, we calculate the weight and bias from the line we drew. The bias is 30, where the line intersects the y-axis, and the weight is negative 3.6. So we're using the format above to basically convert that into this diagram. For instance, using this model, a 4,000 pound car would have the fuel efficiency of 15.6 miles per gallon. Cool, so we can use this line of best fit to predict things. Oh, wow, models with multiple features. Although the example in this section uses only one feature, the heaviness of the car, a more sophisticated model might rely on multiple features, each having a separate weight. For example, a model that relies on 5 features would be written as follows. So we have this here. For example, a model that predicts gas mileage could additionally use features such as the following: engine displacement, acceleration, number of cylinders, and horsepower. This model would be written as follows. So they have these different features in here, and then the weights all with dependence with them. Rivet 10, can we go back to the first lesson? Ah, that was the intro to machine learning. I'm wondering if you potentially joined late. If not, if you did, no worries. I've been jotting down notes throughout. Feel free to go back through the VOD if you'd like. Basically, what we did in the first part was to review what exactly a feature is, what data is, what model is, what the goal of machine learning, and different types of machine learning is. And if you'd like, feel free to follow along. If you click the link in the pinned message, you can go back and click the Intro to Machine Learning course and sort of read through it. Pod transit by basically sort of a weighted average. Yes, no, I think that's exactly what they're going for here. A weighted average with the different types of features. All right, by graphing some of these additional features, we can see that they also have a linear relationship to the label, miles per gallon. Oh, wow. So if we have a displacement with respect to miles per gallon, which is our predicted value, we can also see that there's a bit of a linear relationship here. Okay, or car's acceleration in this case, and its miles per gallon. Also another linear relationship here. Our car's horsepower and its miles per gallon. So yeah, so we basically have many linear relationships, and we're seeing how do these features all combine for us to predict the label. So what parts of the linear regression equation are updated during training? So I guess we are adjusting the bias and the weights. We're keeping our prediction and our feature values the same. We're just adjusting the weights ever so slightly so that we can get the correct answer. Yeah, based on loss. So I think we're going to talk about that next. Yeah, perfect. Loss. Not the meme. Loss. Whew. Okay, let me drink a bit of tea. Don't want my throat to go bad. How are you guys feeling? Thumbs up from the class? Any questions? Any hands in the air? No meme found. Maybe I should make a meme. My hashtag for memes is hashtag ZURREAL. It's like surreal, but with a Z. Maybe I can make a meme for loss and this course that we're doing. Yeah. I think we'll really have to name this course Machine Learning A to Z. I think that would be really cool. I guess another cool fact is before I found this course, another huge shout out to Code Life. She's a coding VTuber. She has been doing a lot of machine learning content. I think she's a software engineer in her free time. In her free time? No, that's like her main time. and she's a VTuber in her free time. But yeah, no, she was the one who suggested this course. She also suggested another one by Free Code Camp, but that one is basically entirely videos, and I did not want to deal with a copy strike. Crypto, no, your brain is liquid. No, you need to freeze it again. Ah! Make it solid again. Yeah, no, one thing that I was thinking about also doing is maybe I can do the 100 days of code. It's a challenge that I've always wanted to do, but I feel like with the Orbeez, I now have an external motivator to do it. We can code something really fun. Or maybe 100 days of building. I do want to get back into soldering and tinkering with things again. So that would be really cool to share as well. All right. How is the class feeling? I hope everybody's feeling good. Let's move on to loss. Loss is a numerical metric that describes how wrong a model's predictions are. Loss measures the distance between the model's predictions and the actual labels. Okay, the goal of training a model is to minimize the loss, reducing it to its lowest possible value. So we have the model here, and these arrows represent the loss lines, which is measured from the actual to the predicted value. So we're trying to reduce these loss lines as much as possible. Okay. Distance of loss. In statistics and machine learning, loss measures the difference between the predicted and actual values. Loss focuses on the distance between the values, not the direction. For example, if a model predicts 2, but the actual value is 5, we don't care that the loss is negative. Instead, we care that the distance between the values is 3. So it's like taking the absolute value. So we don't care about the sign. Thus, all methods for calculating loss remove the sign. The two most common methods to remove the sign are the following. Take the absolute value of the difference or square the difference. So that also gets rid of the sign. Cool. So many different types of loss. In linear regression, there are 4 main types of loss, which are outlined in the following table. L1 loss. The sum of the absolute values of the difference between the predicted and the actual values. Oh, so we're getting into funky math here. Sum of actual minus predicted. Mean absolute error. The average of L1 losses across a set of samples. So we're dividing by the number of examples now. L2 loss, the sum of the square difference between the predicted values and the actual values. Okay. Or we can also divide that by the number of examples for mean squared error. Okay, wow, that was a lot of new vocabulary words. But I guess an easy way to remember that is like L1 doesn't have a square. L2, because it has a 2, is like the square. And then when we have like the mean in front of it, that's when we divide by the examples. I think it'll take some time for me to get this vocabulary in my head, but hopefully that makes sense. Imagine if we end up coding the worst malware in history. Guys, Orbeez, don't give me any new ideas. The malware just... Oh, that's smart. Wouldn't it be epic to have, like, some sort of... Maybe that should be, like, my final ML goal. To make a project that, like, takes in a bunch of surreal memes and is able to, like, generate or predict, like, captions or even better, maybe, like, images for new surreal memes. I can have a machine learning factory. What do you guys think? It's so surreal factory. The ZURREAL FACTORY. How about that? I expect sigmas and deltas. Got only L's here. L for loss. 1 and 2 basically describe, yep, which power to rise. Exactly. Code your own ChatGPT? I mean, that sounds pretty advanced. The people at OpenAI are super duper smart. These are basically L1 and L2 norms. The ZAI. How do you even pronounce that, Crypta? That's funny. Okay, yeah, the functional difference is squaring. The difference between the prediction label is large. Squaring makes the loss even larger. So I guess that is to emphasize what the loss is. When processing multiple examples at once, we recommend averaging the losses across all the examples, whether using MAE or MSE. Okay, cool. Calculating loss example. Using the best fit line, we'll calculate L2 loss for a single example. From the best fit line, we had the following values for weight and bias. Okay, if the model predicts that a 2,370 pound car gets 21.5 miles per gallon, but it actually gets 24, we can calculate that by doing this. Ah, I see. So we use the line of best fit described here to predict that we would get 21.5. The actual value, though, is 24. And so we would say that the loss, the difference, is a prediction minus actual value. So 21.5 minus 24 squared. Okay, that makes sense. Orbeez, are we all good? Does the loss, not the meme, but in linear regression, make sense? It's perfect. It's ZURREAL. Guys, I think that really should be our final project. Making a ZURREAL factory. No international system immunity. Not the pounds, not the miles. It's like that one meme that's like, WTF is a kilometer. That's this. Choosing a loss. Deciding whether to use MAE or MSE can depend on the dataset and the way you want to handle certain predictions. Most feature values in a dataset typically fall within a distinct range. For example, cars are normally between 2,000 and 5,000 pounds and get between 8 to 50 miles per gallon. An 8,000 pound car is outside the typical range and would be considered an outlier. Okay, cool. An outlier can also refer to how far off a model's predictions are from real values. For example, a 3,000 pound car or a car that gets 40 miles per gallon are within the typical ranges. I did not know that. This is very, this course is very car-centric. However, a 3,000 pound car that gets 40 miles per gallon would be an outlier in terms of the model prediction. Ah, I see. Because the model would predict that a 3,000 pound car would get between 18 and 20 miles per gallon. So these outliers can also help us refine our results. When choosing the best loss function, consider how you want the model to treat outliers. For instance, MSE moves the model more towards the outliers, while MAE doesn't. L2 loss incurs a much larger penalty. So I think this was mentioned earlier, because L2 squares the difference, the penalty is much greater. So I think that also changes how the model is trained. For example, the following images show a model trained using MAE and a model trained using, if we scroll down. The red line represents a fully trained model. So with MSE, the model, I see. The model moves the model closer to the outliers. But when we do MAE, so mean average error, which is, mean squared error does the L2. So it squares the difference, which is why these outliers are more important. So it adjusts more towards the outliers. Whereas for MAE, we aren't squaring our differences. So these outliers at the very end are less important for the model to be trained. That makes sense. That's actually really interesting. So we can actually adjust basically what is the influence of these outliers. Yep. MSE, so mean squared error, the model is closer to the outliers, but further away from most of the other data points. So mean average error, where we're not squaring it, the model is further away from the outliers, but closer to most of the other data points. So let's check our understanding. So consider the two plots. So which of the two data sets shown in the preceding plots has a higher mean squared error? So I guess for mean squared error, we want it to be closer to the outliers because the difference matters more often. So I think it would be more so the data set on the left, because this one on the right still excludes these outliers. So mean squared error further away from most other data points. Yes. So that's basically what's being described here. What? What? They actually want us to calculate it? The 6 examples on the line incur a total loss of 0. The 4 examples not on the line are not very far off from the line, so even squaring their offset still yields a low value. What did they say for the right? Oh, did they actually want us to calculate it? Maybe that's why they actually showed it. Maybe that's why they actually showed the grid lines. However, although only 2 points, both of those points are twice as far off. Oh no! I think I misread the question. They were asking for a higher mean squared error. I see. So for the mean squared error, we want to be closer to the outliers. And so in this case, that would be... That's why the one on the right is correct, because we're further away from the outliers, so that would be a higher mean squared error. Sorry, I got it swapped around. So in this example above, it's further away from the outliers because it's closer to the outliers because we trained it with the mean squared error, the squared difference. But this means that we're minimizing the mean squared error. This question wasn't asking for what was it trained on, it was asking for what was higher. So in this case, that would be the one on the right. Oops. Oh, and then that's the end of this course. So we learned about mean absolute error, mean squared error, L1, L2, loss, outlier, and prediction. Cool. So it's probably really good to remember. Probably good to remember and reread the question, class. Reminder to double check your work. All right, next one is gradient descent. I'm actually curious to see how... Oh, this course is basically almost complete. I think we can finish this one out. Oh, also for the people who just joined, I won't be playing these crash course videos to not get struck down by YouTube and my channel eliminated forever. I just don't want to get copy striked. But if you go into the link in the chat, you can follow along. There's actually a tutorial on YouTube to make your own ChatGPT with Python. I traded on my own personal notes. Oh, that's really impressive. And don't call yourself a dum-dum. No one is a dum-dum. Everyone is big brain. Especially if you're here. All the Orbeez are big brains. That would be really cool. Let me actually jot that down. I wonder if there's a way to actually train to make a ChatGPT on Python to make our new ZURREAL factory, or our new factory of ZURREAL memes. Have you ever gradient descended in your life? I did. Yeah, no, me on my commute back home, I always gradient descent. Gradient descent is a mathematical technique that iteratively finds the weights and bias that produce the model with the lowest loss. Gradient descent finds the best weight and bias by repeating the following process for a number of user-defined iterations. So it basically finds what is the best line to describe the data. So the model begins training with randomized weights and biases near zero, then repeats the following steps. Calculate the loss. Oh, so I guess there's a diagram here. Let's follow this diagram. So calculate the loss with the current weight and bias. Okay. Determine the direction to move the weights and bias that reduce loss. Okay. Move the weight and bias values a small amount in the direction that reduces the loss. Return to step one and repeat the process until the model can reduce the loss any further. So we're basically using gradient descent, so we're iterating so that we can describe the line a best fit for the data in the best way that we can by like slowly adjusting the properties of this line. Okay. All right. Let's just take a look at this. So they're sort of walking through. Yeah, you Orbeez can review this probably in your own time. I think it basically goes through the math behind what this training looks like. We calculated the loss in the previous lesson, and I think it will do more to describe what the gradient descent is. Cool. Model convergence and loss curves. When training a model, you'll often look at a loss curve to determine if the model has converged. The loss curve shows how the loss changes as the model trains. The following is what a typical loss curve looks like. So loss is on the y-axis and the iterations are on the x-axis. Ah, I see. So we can see that the loss is sort of like asymptotically approaching zero. That makes sense. Because as we iterate more, as we adjust the weights and biases, the line that describes the data will pass better through the points. You can see the loss dramatically decreases during the first few iterations, then gradually decreases before flattening out around the 1,000th iteration mark. After 1,000 iterations, we can be mostly certain that the model has converged. I'm wondering, I feel like I've seen some examples in Python where a model does not necessarily converge. I wonder what sort of arises that does that. Does that mean that a single line of best fit just cannot describe the data, or a single model cannot describe the data? In the following figures, we draw the model at 3 points during the training process: the beginning, the middle, and the end. Visualizing the model state at snapshots during the training process solidifies the link between updating the weights and bias, reducing loss, and so forth. Okay, so let's actually look at these pictures. So this is the start, where there's a large amount of loss. Yeah, no, this line of best fit here just looks, it does not describe the data at all. So the loss line is really bad. And so after the 400th iteration, the gradient descent has found the weight and bias that produces a better model. So this definitely describes the model a lot better. And near the end, the 1,000th iteration, the model has converged, producing a model with the lowest possible loss. Okay, yeah, and then this line looks like it describes the data very well. So it's basically adjusting that line. Cool. What's the role of gradient descent in linear regression? Gradient descent removes outliers. Nope, that's not true. Gradient descent is an iterative process that finds the best weights and bias that minimize the loss. Yes, that makes sense. Gradient descent helps to determine what types of loss to use when training a model. No. So, definitely the second one. So, gradient descent helps us find the best descriptors for the line of best fit, the best weights and bias. All right, Orbeez, let me check your understanding. How is everybody feeling? Do you think I'm going too fast, too slow, just right? What do you guys think? Okay. Okay, whoa, convergence and convex functions. What? We can do this in 3D? That's crazy. We alive? I hope everybody's alive. To the person who is here at like 4 a.m., I hope that you're still alive, or at least getting some sleep and not being in class. I will give you a hall pass or a absence pass for today. Space Guy Ryan, nice pacing. Okay, good. Ozymandias, think good. Okay, good. Crypta, upside down smiley face. I hope that means good. The loss functions for linear models always produce a convex surface. As a result of this property, when a linear regression model converges, we know that the model has found the weights and biases that produce the lowest loss. If we graph the loss surface for a model with one feature, we can see its convex shape. Okay, the following is the loss surface of the miles per gallon dataset used in previous examples. Weight is on the x-axis, bias is on the y-axis, and loss is on the z-axis. Ah, I see. So as we're adjusting the weight and the bias, which are both aspects of the line of best fit through the data, we are trying to minimize the loss. So the lowest point of this convex structure would represent the weight and bias that would best match the data. Nikki, I took a machine learning or was a data analysis course on CozyEra before. Oh yes, no, there are plenty of courses on CozyEra. I actually recently took one on scientific writing, and it was really useful. I feel like it really helped me like rethink about sort of my habits in writing, whether that was adjusting like the time I allocate for writing. I think I'm the type of person who prepares a lot when writing and not necessarily like actually do the writing. So I do a lot of preparation, and then maybe in like one random night I just like sit down and like churn out all the writing. But the course actually described like more sustainable ways of writing. They also gave like really great tips on just like basic grammar and like structuring and how to write grants and that kind of stuff. So that was really interesting. Okay, in this example, a weight of -5.44 and a bias of 35.94. Okay, so we're basically finding the lowest point of this convex surface. Oh, the loss surface, I guess is what it's called. A linear model converges when it's found the minimum loss. Paul Senpai, is the ddx equals 0 of the curve the point that we are searching? Yes, I think that's sort of what it's going for. But would ddx even be able to describe the data? Because in this case, it would be three-dimensional. I feel like you would have to have find the point where all no, just an x and y would give a slope of 0. But yeah, it's just a local minimum. Yeah, the partial derivatives, Nikki. Yeah, that was what I was thinking of. Okay, a linear model converges when it's found the minimum loss. Therefore, additional iterations only cause the gradient to move the weight and bias values in very small amounts around the minimum. If we graph the weights and bias points during a gradient descent, the points would look like a ball rolling down a hill, stopping at the point when there's no more down slope. So these points represent what we're sort of approaching with many iterations. We're sort of reaching this lowest point here. Yeah, showing the gradient descent points stopping at the lowest point along the graph. Notice that the black loss points create the exact shape of the loss curve. Oh, interesting. So if you look at this as a two-dimensional slice through this plot, that looks exactly like this plot here on the left that we had before that describes the loss curve of the data. That's because it's just before it was iterations with loss. Now we're having weight and bias with loss, and we're sort of going through each iteration. That makes sense. That's really cool. Where were we? I think we were right here. Yeah. It's important to note that the model almost never finds the exact minimum for each weight and bias, but instead finds a value very close to it. It's important to note that the minimum for the weights and bias don't correspond to 0 loss, but only a value that produces the lowest loss for that parameter. Using the weight and bias values that produce the lowest loss, in this case, a weight of negative 5.44 and a bias. Okay, so we're basically saying, okay, we ran this a ton of times. We found what the best weight and bias are that minimize the loss, and that line is here, which seems to be going through pretty well. So this could be the best model for the dataset because no other weight and bias values produce a model with lower loss. Great. So next up is hyperparameters. Okay, let me take a quick look at the chat. So the trade-off could be a certain perfect solution, but a high computational weight on the increase of data. Yes, so let's say that every step that you're taking with gradient descent is super duper small. Then I would assume that you would have to run it many, many more times. You would get a very precise solution, but you would have to run it many, many more times as it takes smaller and smaller steps. Now, what I'm sort of thinking about is what if you start off with big steps, and then those steps get increasingly smaller and smaller and smaller as you approach the correct solution. I guess either way it would probably still be more computationally heavy, as I guess that could lead to an infinite loop, wouldn't it? Because if you keep getting smaller and smaller, smaller and smaller steps, would the steps become infinitesimally small? And it would converge on a more precise value. I guess you can set a lower limit to how small the steps would be. M-Champ, yep, that's the thing. I forgot what it's called. Yeah, okay, so so this idea isn't fully crazy. Yeah, mean square error makes it even worse, I guess. Yeah, there are algorithms with varying step size. Yep, I wonder if any of the Orbeez know if there's an actual name for that algorithm. That might be really interesting. I think they're just describing gradient descent here just to make it easier for us. Okay. All right, next up, linear regression, hyperparameters. Hyperparameters are variables that control different aspects of training. 3 common hyperparameters are learning rate, batch size, epochs. Epochs? Epochs, I think. How do we pronounce that? Epochs? I should know this. I feel like I'm the type of person that struggles at saying some basic words. But I think epochs is not a basic word. In contrast, parameters are the variables like the weights and bias that are part of the model itself. In other words, hyperparameters are values that you control. Parameters are values that the model calculates during training. Okay. So we're now saying that parameters are like weight and bias. Wow, a lot of vocabulary words. Hyperparameters sounds super epic though. Like imagine being like, having like hyper stuck to the front of your name. Like, you know, there's like supernova, there's like nova, supernova, hypernova. I think that's an actual thing. All right. Don't want to get too distracted. Okay, first, she speaks Zinglish. Yes, I think my language is Zinglish. I think there was a study done that was saying that like people who develop their own sort of a micro dictionary or micro language tend to have like better well-beings or something like that. I mean, I think I have like a micro language. I speak in the language of ZURREAL memes. Hyperparameters, my hypermodel for hyperprediction. Doesn't that sound epic? Imagine somebody being like, yeah, what is your machine learning project on? Oh yeah, hyperparameters. Well, I guess in reality they're probably not super cool, but all right, class, we don't want to get distracted. Focus, lock in. Learning rate. Learning rate is a floating point number you set that influences how quickly the model converges. If the learning rate is too low, the model can take a long time to converge. However, if the learning rate is too high, the model never converges, but instead bounces around the weights and bias that minimize the loss. I see. So this is also probably dependent on the step size as well. Or is the learning rate also the step size? Because, or maybe they're correlated, but they're not exactly the same thing. Let's keep reading. The goal is to pick a learning rate that's not too high nor too low so that the model converges quickly. The learning rate determines the magnitude of the changes to make to the weights and bias during each step of the gradient descent process. The model multiplies the gradient by the learning rate to determine the model's parameters for the next iteration. So the model multiplies the gradient by the learning rate. I see. So that the learning rate basically is sort of the step size as we approach our correct weights and biases. In the third step of the gradient descent, the small amount to move in the direction of negative slope refers to the learning rate. Okay. The difference between the old model parameters and the new model parameters is proportional to the slope of the loss function. For example, if the slope is large, the model takes a large step. If small, it takes a small step. For example, if the gradient magnitude is 2.5 and the learning rate is 0.01, then the model will change the parameter by 0.025. It's proportional. I guess that could also be a big difference. The ideal learning rate helps the model converge to a reasonable number of iterations. So, okay, let's see this example. Loss graph showing a model trained with the learning rate that converges quickly. Oh yeah, no, that flattens out like immediately. In contrast, a learning rate, but the thing is the loss is not fully minimized, I think. Shouldn't it be much closer to 0? Maybe it's because it converges quickly that it doesn't get the correct answer. In contrast, a learning rate that's too small can take too many iterations to converge. In figure 22, the loss curve shows the model making only minor improvements after each iteration. Loss graph showing a model trained with a small learning rate. I see. In that case, it will take way too long for the model to converge. Oh, M. Champi. I think it's called learning rate decay, where the steps get smaller and smaller. I see. Well, I guess that makes sense because we're literally learning about learning rates right now, and that sort of seems like the step size. Yep. Could the learning rate be the slope of the tangent curve in a given point in the loss curve? I think that's what they're describing here. They're saying one thing that you could do is say that the slope is large and the model takes a large step. So if you do the slope of the curve, you can adjust the learning rate to match the ideal weights and biases. I think that's what it's trying to say. A learning rate that's too large never converges. Oh yeah, no, I've seen plenty of these plots. This is not fun, because each iteration either causes the loss to bounce around or continually increase. So in this case, the loss, oh yeah, no, this definitely bounces around, doesn't converge, it doesn't flatten out. Loss graph showing a model trained with a learning rate that's too big, where the loss curve fluctuates wildly, going up and down as the fluctuations increase. So that was this one. Loss graph showing a model trained with a learning rate that's too big, where the loss curve drastically increases in later iterations. Oh, so if we have a learning rate that's too big, it can actually make things much worse. So it's actually really important for us to set the learning rate correctly. Ozymandias, yes, the learning rate determines how big the steps are relative to the gradient at a point. Yep. Sean P, yeah, I think you start with large steps and then move on to smaller steps. Yep, no, that makes sense. I think that was sort of what I was thinking might be the best. Ozymandias, with a constant learning rate step, sizes will naturally decrease as the gradient becomes less steep. With a constant learning rate. So the step sizes will naturally decrease as the gradient becomes, yeah, so naturally we would sort of refine and tweak our measurements only by a little bit to get the ideal weights and biases. Oh, what is the ideal learning rate? 0.01. The ideal learning rate is problem dependent. I think it's problem dependent. Like, what does it mean by 1 or 0.01? I think you want a learning rate that's just right for your problem. Hopefully this is right. Oh, okay. Each model and data set will have its own ideal learning rate. Cool. Yeah, no, that was really interesting. I think that really tied back in with, like, sort of the idea of, like, gradient descent in the previous lesson. Yep, it's got to be problem dependent. Okay. Batch size. Batch size is a hyperparameter that refers to the number of examples the model processes before updating its weights and bias. You might think that the model should calculate the loss for every example in the dataset before updating the weights and bias. Okay, so the number of examples. Okay, however, when a dataset contains hundreds of thousands or even millions of examples, using the full batch isn't practical. Two common techniques to get the right gradient on average without needing to look at every example in the dataset. So we basically choose a tiny batch of the data to update our gradient descent. Our stochastic gradient descent and mini batch stochastic gradient descent. Mini batch, that sounds really cute. All right, let's see what these are. Stochastic gradient descent. Stochastic gradient descent uses only a single example. One example. Oh, per iteration. Given enough iterations, SGD works, but is very noisy. Noise refers to variations during training that cause the loss to increase rather than decrease during an iteration. The term stochastic indicates that one example comprising each batch is chosen at random. Whoa, so you literally just choose one at random? I feel like, what if the one you chose was like an outlier? Well, I guess since you're doing many iterations, then over time that would sort of even out. Or is that why it leads to noise? Because you might choose a value that's like an outlier or may not necessarily be close. Notice in the following image how loss significantly slightly fluctuates as the model updates its weights using SGD, so stochastic gradient descent. Okay. Okay, so yeah, let's look at mini batch. Mini batch stochastic gradient descent is a compromise between full batch and stochastic gradient descent. For n number of data points, the batch size can be any number greater than 1 and less than n. The model chooses the examples included in each batch at random, averages their gradients, and then updates the weights and bias once per iteration. So determining the number of examples for each batch depends on the dataset and the available computational resources. I see. So you basically, instead of just doing one, you can choose like a handful of them, depending on how much resources you have. I guess that would diminish the noise by a lot. So in general, small batch sizes behaves like stochastic gradient descent, and large batch sizes behaves like full batch. So you can sort of pick and choose like what direction you want to go into. Maybe if you have like a lot of computational resources, you can choose almost all of the data set to train the model. Whereas if you don't, you can do maybe like a small batch or a handful instead of just doing one. Does it mean that the direction of the single step is stochastic? I guess, yes. I think like what they're saying is that the direction of each step is dependent on the batch that you have. So in the case of a stochastic gradient descent, you would literally have one data point. So the direction of the step that you're going in, so the changes that you make to your weights and biases would point towards that one stochastic value. While training a model, you might think that noise is an undesirable characteristic that should be eliminated. Oh, however, a certain amount of noise can be a good thing. I didn't know that. Huh. I thought noise was always bad. In later modules, you'll learn how noise can help a model generalize better and find the optimal weights and biases in a neural network. Oh, that sounds so epic. We should definitely get to that. All right. Epochs. During training an epoch? Is it epoch? Orbeez, do you guys know? I think it's epoch. Z struggling to pronounce, like, words. Okay, during training, an epoch means that the model has processed every example in the training set once. For example, given a training set with 1,000 examples and a mini batch size of 100 examples, it will take the model 10 iterations to complete one epoch. Okay, so it is epoch, according to Alexander Babsky. Epoch. Yes, epoch. Very pog. Training typically requires many epochs. So it basically takes the gradient descent, the mini batch or stochastic gradient descent that we did to describe these epochs. Training typically requires many epochs. The system needs to process every example in the training set multiple times. The number of epochs is a hyperparameter you set before the model begins training. In many cases, you'll need to experiment with how many epochs it takes for the model to converge. In general, more epochs produces a better model, but also takes more time to train. So it is a trade-off. You want to get a better model, but maybe you don't have as much computational resources. So if you have a very tiny batch, you would have many epochs. Yes, so one epoch. Oh no, one epoch would then be many batches. I see. Full batch versus the mini batch. Okay. The following table describes how batch size and epochs relate to the number of times a model updates its parameters. Okay, so if we have a full batch, so if we're using the full batch to update the weights and biases, after the model looks at all the examples in the data set, the model updates the weights and biases. Okay, so for instance, if a data set contains 1,000 examples and the model trains for 20 epochs, the model updates the weights and biases 20 times, once per epoch. Okay, that makes sense because it's using the full batch every time. So if we have stochastic, after the model looks at a single example from the data set, so if a data set has 1,000 examples and the trains for 20 epochs, the model will update the weights and bias to 20,000 times. So we have 1,000 examples and we go for 20 epochs. So we adjust the weights and biases 20,000 times because we are adjusting it once for every example we're looking through. So if we have the mini batch, we are looking at a sample of batches. For instance, if a dataset contains 1,000 examples and the batch size is 100 and the model trains for 20 epochs, the model updates the weights and bias 200 times. I thought it would be 2,000 because for every epoch, because you're going through 100 for every epoch. Is that not correct? Or do we have to somehow like divide or something like that? So maybe if a data set contains 1,000 examples and the batch size is 100, so every time you're going through, oh no, the way that it works is we're going through 100, which is like, we would have to go through the batch 10 times to look through all 1,000 examples. And so if the model were to train for 20 epochs, it would basically go 20 by 10 to go through the entire data. So the model would then update the weights and biases 200 times. Yeah. Okay, let's see. Exercise, check your understanding. What's the best batch size when using mini batch SGD? It depends on the situation. Yeah. Depends on the data set and the available computational resources. So which of the following statements is true? Larger batches are unsuitable for data with many outliers. Doubling the learning rate can slow down training. Large batches are unsuitable for data with... I feel like it would be better if we have larger batches. Because if we have larger batches, then we can actually even out the outliers. But if we double the learning rate... Wait, no. If we double the learning rate, that means that our step size is larger. Would that slow down training? I feel like that would actually make it faster. Wait, larger batches are unsuitable for data with many outliers. Larger batches. Larger batches are unsuitable. I think, yeah, that's what I thought too. Doubling the learning rate would speed up training. Yeah. Or, yeah, I thought doubling the learning rate would speed up training. Or at least give it bigger steps. It would slow down training and cause more variables. Larger batches are unsuitable for data with many outliers. I thought larger batches would be better for many outliers because, oh, yeah, maybe larger batches may dilute outliers, maybe. Yeah, no, I feel like I'm totally lost on this one. Doubling the learning rate can slow down training. Here, let's actually just go back into the text. So when we looked at the learning rate, it says that if the learning rate is too high, the model never converges. Yeah, no, if the learning rate is too low, then the model can take a long time to converge. Yeah, I think the first one is less true than the second one. All right, let's click the second one and see what we get. Oh, huh, interesting. This statement is true. Doubling the learning rate can result in a learning rate that is too large. And therefore, so when it means slowing down, it's not saying... When I was thinking about doubling the learning rate, I thought it would take bigger steps to the correct answer, but it would actually bounce around. So, increasing the amount of time needed to converge. I see. Yeah, and then if we click the first one just to see, larger batches, yes. By averaging more gradients together, larger batch sizes can help reduce the negative effects of having outliers in data. So I think like what was mentioned, larger batches may dilute the outliers. Yeah, that makes sense. Okay. Yeah, that was a bit of a tough one, but I think that makes sense. We want the perfect learning rate so that it can approach the correct biases and weights, but also it just doesn't bounce around. All right, so we got all of these. Oh, the next is a programming exercise. I hope it's in Python. I actually haven't checked. Oh, it would require me to use the collaboratory platform using the Keras library. Let's take a look at this. Now available for JAX, TensorFlow, and PyTorch. Okay, I've actually not heard of this before. The collaboratory platform. Run directly. Is there a way to... Alright, give me one quick second. I'll check this out and see if I can load it up. Oops, wrong screen. Alright, this is the right one. So it looks like it's a Google Colab notebook. this is really great, but maybe do you guys want to save? It's a bit long. How about we save this one for the next stream? And for this stream, we can do the quick quiz and let's see. Yeah, we can finish up with the quick quiz, and I think that will be all for this stream. And then for the next stream, we can actually do some real linear regression coding. How about that? Okay. When do you get back from your break again? So I will be back in a few weeks. So the real reason why I'm leaving is because I'm traveling for a bit and I won't be able to live stream. I will be back, I think, mid-September. I will post an announcement, sort of doing like a welcome back stream. I know, it's so sad. I'm glad that I was able to chat with you Orbeez and get to know you guys though before I left. And don't worry, this is not goodbye. During this time that I will be gone, I will be posting my brand new explainer series, which I've worked really, really hard on. It is my blood, sweat, and tears. It is my child. And my goodbye stream is on Friday. And I will have a few surprises and announcements for you guys. So don't worry, things will be all good. But it also means that for homework Orbeez, you guys will have to review these videos and these assignments. Yeah, no, I know. I'm going to be gone for a whole month, but I promise you, I'm going to very, very epic places. I will send many photos. You guys will be really surprised. Here's a hint. I might be able to get some real Hololive merch. I think that was a pretty dead giveaway as to where I might be going. I know, I'm also very sad about leaving. But I hope you guys will enjoy my new explainer video series. And when I'm back, I will continue with the live streaming, just as usual. We'll keep going through the machine learning course and so forth. My character is not good at expressing sad emotions, but I have a very sad facial expression right now. Sag. It's okay, Orbeez. I'll still be online on Twitter, X, and everything. I'm not disappearing. I'll just be off of just live streaming. But it's okay. That means that this last week means that we have to learn max. We have to plump up your brains and make you guys super big brain before I leave. And then you guys will also have these videos to look back on and review. And so the next time I see you Orbeez better be in the most big brain state that I've ever seen. Oh, you'll find us here. Oh, that's so sweet. Yeah, I'm really sad to be leaving, but it's all right. I am super excited to tell you guys about all the adventures that I'm going to go to. And it'll also mean that I'll be also able to share some of the photos and epic adventures that I've had at my current location, which will be super cool to share as well. Okay, let's finish up with this quiz, and I think that would be all good. So, moment of truth. Let's open the... Oh, that scared me. Oh, thank you, Ixius Masaki, for subscribing. Welcome to new Orbeez. Okay, let's test our knowledge. You must answer at least 4 questions correctly to pass this quiz. And there's 5 questions. There is no room for error. Which of these is an example of a parameter that is calculated during training for a linear regression model? Weight, learning rate, prediction, and label. We need to calculate the weight, learning... What? Wait, hold up. That is calculated during training. Maybe I'm thinking too much into this, but don't we adjust the learning rate basically off of each training? We don't change... Oh, we know. We get what the label is, of course, because we're trying to calculate the label for each time. See, look at this. This is Z overthinking again. I'm Zoverthinking. So we're calculating the label for each time and adjusting, finding the loss with the model, depending on how we calculate the label. Yes, learning rate is a hyperparameter. Yep, that we set that in advance. Okay, suppose you are building a linear regression model to predict the sale price of a used car. The training dataset includes the following information: sale price, model year, MSRP, odometer mileage, gas mileage. Z's weakness is cars. Ah, do you guys want to do polls? How about that? Wait, this one is a fill in the blank though. This one's a fill in the blank. I could do a poll with like every single word. How many weights? For this one, just type it into the chat. What do you think? Let me reread the question. How many weights will there be for this model? So I think the number of weights is dependent on the number of features, because the equation is like B plus weight times X. So we have the model year, MSRP, odometer mileage, gas mileage. So 1, 2, 3, 4. So four weights. And we use those to predict the model. 1, 2, 3, 4. Okay. Oh, do I have to enter like a word? Can I just enter 4? Or do I have to spell it out? 4? I think just 4 is fine. They should probably accept both. If they don't, I'm gonna throw a hissy fit. What is the mean squared error? Oh. Oh lord, we gotta calculate this guy. Oh, well this is easy because all of the points are on the line. So in this case, we have okay, so let's calculate this. In this case, we have 2 points, both of which are a difference of 2 away. So when we calculate this, we square the error. So in this case, that'll be 2 squared plus 2 squared. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points. Isn't it the same? Was it 0.4? Am I calculating this incorrectly? I thought it would be 2 squared plus 2 squared over 10. 8, 10. I thought it would be 0.8. Or before it said 0.4. Is that correct? 2 squared. Mean squared error. It meant the same curve. I meant the same curve of the examples. The same curve of the examples? This one? Or oh, you mean like in the previous lesson. I mean, it was there. I mean, we could check it out. I think there was the chapter before where we saw that. Ah, it was this one. No, it's cheating. All right. Okay, Orbeez. Instead of going back, we're not going back. Okay, Orbeez, what do you guys think? Try calculating it on your own. I think it's Oh, I just thought the mean squared error would just be the vertical error. I just thought it was 2 squared plus 2 squared over 10. So 0.8? Orbeez, what do you guys think? While you guys calculate, I will skip this one and we can move on to the next one. Which of these controls the size of the steps of the gradient descent algorithm? We just conversed about this, the learning rate. Suppose you're training a linear regression model and after about 100 iterations, you notice that the loss is high and trending downwards, but not by a significant amount. The loss is high and is trending downwards, not by significant amount. What is likely the problem? In that case, wouldn't the learning rate be too small? Oh, okay, wait, sorry. I forgot to do a poll this time. So for question 5, do you guys think it's A, B, C, or D? Here, let's do this poll. What do you guys think? Here, let me scroll. Yep, so far for B. I think it's also B as well. In that case, the the data isn't moving enough. I mean, each step isn't large enough. And so over time, we're not able to learn as much. I think it's too small because it's going in the right direction, but very slowly. Yes. Okay, let's go back to this one. What do you all think? I did 2 squared plus 2 squared over 10, which was 4 plus 4 over 10, so 8/10, so 0.8. All right, we can end this poll. What do you all think? I think it might be 0.8. Should I just put it in for now? All right, I think we should go for it. All right, let's double check our work. So we said that a label is calculated during training for a linear regression model. We said that in this case, the training data set, we would have 4 weights corresponding to each of the features. 0.8 for this one. The learning rate controls the size of the steps, and the learning rate is too small. Let's see. 4 out of 5. What? Wait, I did not expect getting this one incorrect. Which of these is an example of a parameter that is calculated during training? Aren't we calculating the label every single time? Oh, or would it be weight because we're actually calculating what the weight is for the linear regression? Yeah, it would be the weight. I wonder if there's a way to like... We cannot even retake it. It's okay, we passed though. We have passed the quiz. I wonder if there's a way to... Oh. We can retake it so that we can get a 5 out of 5. I don't know if we can do that. Boop. Ah, yes, we can. So in this case, we would say that it's over. No, it's okay. We're so Zarok. It's okay. It's okay, guys. Which of these is... Wait. It's okay, we passed. We passed. We said this was 4. The mean squared error was 0.8. So this is correct. And then which of these controls the size of the steps of the gradient descent algorithm? We said the learning rate. And then the learning rate is too small. Yay! We passed the quiz! Let's go, Orbeez! We're so Zarok. It's like worse. Oh no, I heard the crazy one. So there's we're so Jover, we're so we're Joe K, we're so Barack, and then there's one that's like don't cry because it happened, or no, what was it? Don't cry because it's Jover, smile because it Kamala happened. some crazy stuff like that. Okay, we can close out of this. Let's see what's next. Okay, congratulations on finishing the module. We encourage you to explore the various MLCC modules. Okay, so the next one's logistic regression, but I think that should be all for today. In our next episode, how about we go through this code read dataset. Ooh, I see. How about we go through this together? I think that would be great for next time. And then we can keep on learning this course. How about that? I hope you guys were able to learn at least something. I'm a total beginner at machine learning, if you haven't been able to tell already. But I feel like it's so great just like learning with you guys and learning together. Sounds like a plan? Amaterasu? Okay, great. Yeah, no, and thank you guys so much for being here. Here, let me close out this window. All right. Yeah, no, and if you enjoy this series, be sure to like updo, comment, let me know. I know that this is a little bit different from my other streams in that I'm hoping that this can be a little bit more like hopefully like a series. And it would be really great to just learn together. Nice lesson, linear and simple. Yeah, no, I'm glad you guys enjoyed it. And maybe this can actually be part of 100 days of code? Do you guys want me to start doing that as well? So what 100 days of code is, it's created, I think, by, I actually don't know who created it, but it's sort of posting every time you code. You tag 100 days of code and what we've worked on. I think it would be really cool to have a log like that where we do like 100 days of code, but we're basically working through this machine learning course. I mean, I don't think this will take 100 lessons to cover, but I think it would be really cool to have an entire course, go through this entire course, go through its lessons, and then at the end work on our ZURREAL factory, our ZURREAL machine. I think that would be really epic. Oh, hello, Malu. Yeah, no, you just arrived when it ended, but don't worry. This VOD will be up. I will have the timestamps ready, and I will also have notes for you guys. Where would you guys like me to send them? I think it would be great to have them on maybe I can just link them in the description and have them be a file on Google Drive. How about that? Ricardo Bergen, sounds like a plan. Thanks for the stream. Yeah, glad you guys enjoyed, and I'm so excited to do more streams like these. Be sure to update and do all the following. And I also have some really cool photos to hopefully share with you guys of the adventures that I've been having and the adventures that I will have. But until then, I will see you guys on Thursday for our next class, which will be basically working through this Python notebook. And I guess, let's see what it's about. Basically training a model to predict the fare of a taxi ride in Chicago, Illinois. How about that? It'll be our first coding experience together. Yes, this was fun. Thank you so much. Okay, I think that's all from me today. Everybody have a good night, afternoon, morning, whatever time zone you're in. Keep on learning, keep staying big brain. And until next time, I will Z you guys later. Bye. Be sure to subscribe. I am watching you. Bye bye, everybody. Subscribe now. Alright, the next time I see you guys better be super big brain. Alright, see you guys on Thursday. See you later. Bye bye.